Hi, my name is James Yoder, and I'm a graduate student in the Aerospace Engineering Department and a member of the UT Radio Navigation Lab under Dr. Todd Humphreys, which is associated with the WNCG. Today, I'm going to share with you our group's recent work in the tight coupling of visual and inertial sensors with carrier phase differential GNSS positioning. Microaerial vehicles, or MAVs, are increasingly being used for applications which require precise, that is, centimeter-level accurate, position and orientation relative to a global coordinate system, and may also be required to maneuver close to obstacles which block the view of GNSS satellites. Traditionally, carrier phase differential GNSS, or CDGNSS techniques, can provide this highly accurate, globally referenced positioning information. But the use of the carrier phase as an observable requires the resolution of so-called integer ambiguities, which requires advanced statistical techniques and, without a tight position prior, a large number of signals to confidently resolve. The availability of these fixed integer solutions is therefore usually limited to areas that have a clear view of the sky. In this work, we explore the tight coupling of an existing visual inertial positioning technique with CDGNSS. In this architecture, a central pose estimation filter receives RTK position and attitude measurements, inertial measurements, and pixel error measurements of features tracked by a camera. The pose estimates from this filter and their associated covariance are then used as priors for the integer least squares problem, which is solved by the RTK estimator. The visual positioning method we use is based on an existing algorithm called ROVIO, which is a filtering-based SLAM technique which tracks and maps the 3D location of small patches of pixels corresponding to interesting features, which are extracted and stored at multiple scale levels. The GNSS signal processing starts with an advanced software-defined GNSS receiver, which has been heavily optimized for carrier phase positioning in difficult urban environments. Downstream of this receiver, which produces code and carrier phase observables, the RTK estimators use a single epoch integer ambiguity resolution strategy. This makes the estimators insensitive to cycle slips, which is critical to achieving high RTK availability and reliability in an urban environment, where multipath and non-line of sight receptions are common. When the RTK estimators operate without visual inertial aiding, which we call loosely coupled, and during initialization of the tightly coupled estimator, this state propagation occurs inside each RTK estimator using a very simple motion model. So in that case, the RTK estimators are unaided. Information only flows one way, from the RTK estimators to the central pose estimator. When operating in the tightly coupled mode, the internal filter inside the RTK estimators has its propagation step replaced with the propagation step of the central pose estimator. In this way, information from the IMU and the camera can help act as a constraint for the RTK estimators. We first evaluated this system on a set of data captured in open sky conditions, into which simulated GNSS signal outages were injected. Visual inertial tight coupling shows a clear improvement in both the integer fix rate and positioning error seen. This is a case study of the system performance on one small section of a larger real-world dataset. This dataset was captured on the roof of a parking garage next to a building with an overhanging eave, where the rover passes from an area with a clear view of the sky to underneath the eave, causing outages of all but a few GNSS signals, and then moves back to an area with a clear sky view. Tight coupling increases the availability of validated RTK integer fixed solutions for an equivalent probability of false alarm setting in the RTK estimator. Inertial-only tight coupling is unable to provide a strong enough positioning constraint to improve the RTK availability, showing the importance of visual measurements. On this particular dataset, unaided RTK was able to produce a fixed solution 55.3% of the time, and an incorrect integer fix was seen in one section of the data. When incorporating visual inertial aiding, the availability increased to 75.5%. This shows that tightly coupling visual inertial pose estimation with CDGNSS increases centimeter accurate positioning availability under difficult GNSS conditions such as urban positioning. Thanks.